Okay, so tomorrow will be our first quiz, and then I noticed that take a look. Next week, next Wednesday, will be our 校际活动周. So maybe it's a holidays, right? So it seems to me I cannot finish chapter 3 for within 4 hours, right? Today 2 hours, next 2 hours, next week's 2 hours. So it seems like we cannot have our midterm 1 in the midterm week, right? So suppose it should around 15 of April. April. Suppose 15 of April or 22, I don't know, but maybe just it won't be 8th of April. Okay, it won't be 8th of April because we don't have enough time to finish chapter 3. 好，中文就是我们不可能会在4月8号的时候会有期中考了，因为应该是交不完，因为我的下礼拜3是什么什么放假嘛哈，所以说我们就只有4小时，我也想应该是上不完33到34页的投影片。那理论上来讲，那就是4月8号我可能会再讲一点，反正我就4月8号那一周的正常上课，可能是4月15号或者是22号，应该是15号了哈，应该是15号，理论上 ，All right， 所以我们再确认这样。So now let's continue our lecture, and we will proceed to chapter 3. Chapter 3, torsion. Torsion, you know what does that mean, right? You will twist something, you will give torsion on the object. So we will talk about what is twist and the stress-strain relationship in circular rods after torsion, and also torsion and shear, and also relation between E and G. Remember that E is Young's modulus, G is shear modulus, and then remember we had we wrote the equation which connecting between E and G, and I said I will prove that later, right? So today, I mean maybe not today, this chapter we will give you the proof and also tell you what is torque and power, horsepower, or strain energy. All right, so introduction. We define the torsion. The torsion usually apply on the bar called shaft, 轴, okay? So a rod is acting upon by torque. So you can, maybe use your motor 马达, okay? Or maybe your hand or something. Right. So typically we will write down a symbol with 2 arrows, double arrows. Okay, double arrow means the torsion, and then you can imagine that this is a bar, right? And then you get the imaginary couple. Pairs of force couple, P2, P1, P1, P1. Okay, so it looks like a rotation to twist the bar. Okay, and you notice that you can use the right hand rule like this. Okay, so you can using this P here, P2. So your the first finger, okay, point to the right hand side, which means that the torsion is toward you and then go back to the monitor. And then the other one is that it toward you from bottom and then going to the screen on the top, which means that you have your torsion symbol point up to the left. All right, so using your big finger, okay, to write down the torsion direction, okay? And T1 equal to P1 D1. I mean, this is P1 is the force and D1 is the force arms, right? Force arm. So you have D1 between each other. So you got the P1 times D1. But typically we just let you know how the T1 is. And you can see that this is force and then this is meter, okay? Force, Newton, and meter. So the unit of the T1, just like a moment, okay? Just like moment, all right? So let's talk about pure torsion. The torsion, the torque corresponding to each cross section in the member is the same. What does that mean? Okay, you can imagine that you have a bar here, and then you apply the torsion on the two ends of the bar. The first end is to the left hand side, the other is to the right hand side. So you can kind of doing this, all right? Doing this, okay? And then when you do this, you can think about this just like a twist your towel, 毛巾, your 毛巾, okay? And then we can imagine that when you twist it, you can think of that actually the left hand side is kind of stopped, okay? And the other is twist. Although it looks like this, but actually if you stop fixed to the left hand side, if you twist it, actually it has opposite torque between the right hand, my right hand and the left hand, right? Because you just fix it, you twist it, but actually you fix it, you have the opposite and the same values torsion with my right hand, okay? So kind of like this, right? So you can imagine that this is fixed. The left hand side is fixed. Okay, this is the fixed. This area is fixed. This area is fixed, okay? And right hand side is twisted. Okay, this is twisted, okay? And the middle, you can think of this one, all right? So let's take a look. Let's think of the angle of twist. So you imagine that this surface is fixed by my left hand side, left hand, by my left hand. So there's no rotation at that point because it is fixed. So you can imagine that, okay, this is the origin of the cross section, and this is R, right? This is the radius, and then this is the Q point. The Q point at the beginning before the load, but the Q plane means the displacement change, the Q change their position, but because this is fixed, right? So the Q and Q plane are at the same. I guess you can understand this. Q and Q plane at the same point because it's fixed. However, if you twist to the at the right hand side, okay, right hand side, and you found that your Q previously at here, but you after the twist it become here. So there is a open angle change from this point to this point. So you can imagine that this doing like this, right? So kind of make a sort of torsion, right? So your Q point become Q plane, and there is a angle of twist phi, okay, the phi, and you notice that this is phi, so this is phi, right? But here there's no angle between Q and Q plane. So which means that there must be a gradual change of the phi in between. So you can see that it is a gradual change. So Q and Q plane must be slightly opened in between until it go to the end, Q to Q plane, right? So in this area, in this cross section, the Q to the Q plane, just a smaller, relatively smaller phi x. Okay, phi. So you can see that the phi is a function of x. It changes along the x. Okay, so when x equal to 0, the phi equal to 0. So in the middle, it is phi of x. But for the phi L, okay, here I will give you one correction. Phi L is phi L, right? So phi L is a value, but phi of L means that the x equal to L. What is the value of phi? Which is phi L, right? With the small letter. And you can see that I will give you a hint that it is a scalar, 数值, and this is the function. Okay, this is a function of x. So don't confused between these two. All right, be careful. So now you can see that the cross section, at each cross section, they will have different phi, different opened phi angle, twist angle from Q to Q plane. Even at the x equal to 0, there's no angle, no twisted angle. So this twisted angle phi is a function of x. So if you can understand this, we can proceed. And okay, because this is phi is angle, right? So our unit is radian. Okay, this is radian. I will just use radian in mechanics of materials. It's easier for us. Now, if you can accept that, let's proceed further. Okay, so torsion deformation of a circular bar. Okay, so this is similar bar we see that in the previous page, and if we just cut it at the front, and which means that our torsion is uniform in the middle, just like P equal sigma equal to P divided by A in the chapter 1, right? Chapter 2, maybe. So we select the middle part, so we can know that the torsion is uniform in the bar. Okay, then if we cut it and then we show this here, okay, of course, left hand side has the torsion, right hand side has the torsion, of course, and then if we cut this has dx, small segment of this, okay, and then again we want to see the change of d phi. We want to see the change of d phi. So you see here is this surface has their own phi x. This surface has their own phi x plus dx, right? So the change of the change between these two surfaces, the torsion change, the angle of twist between these two sections is d phi. OK, change of 好，那讲中文我觉得开始有点绕口令啊哈。总之我们就切了一段叫 dx， OK， 然后我们想要看看这一个面跟这一个面它的 phi 的转角的差距有多少 ？OK， 左边的转角是多少 ？phi x 嘛，对不对哈？右边的转角是 phi。扭转角是 phi x 加 dx 吧，那这两个差距 就是我们的底 phi 咯 OK so if you can accept that we can say okay this angle new torsion angle of twist here from here to here is d phi okay so if you can understand this let's take a look so if you have you can see that this d phi is b going to b plot right b going to b plot b plot so if we take a look of a surface element, you see this dotted element. There's a dotted, right? This dotted area we call surface element. And before the twist, it looks like a square, right? Sorry, rectangle, 长方形. But after you twist it, your B become B plot, your C becomes C plot, and it looks like this one. And AD the same, right? So it looks to us, it just looks like this is A, this is B, C, D. But now it become A, B plot, C plot, D. So you can see that surface element changed from rectangle to this shape, 平行四边形 okay? So, okay, so this is D, right? And let's take a look. Let's write down. So I want to see the ABCD shape become the AB plane, C plane, D shape. The change of the angle. The change of the angle is we call gamma mix. The reason why we call it mix, we will explain this later. Okay, I will explain this later. You accept that this is gamma mix at the moment. All right, we just say we want to determine the gamma mix by this triangle. Okay, and you can see this triangle is actually this triangle, right? So B and B plane you can determine by the other triangle, yellow triangle, or you can call this pizza shape, Okay, so the gamma mix equal to how to say that? So I will say BB plane divided by AB, right? So you can use BB plane divided by AB, or you can say AB plane, but actually they are quite similar. You can treat that as a pizza shape, okay? So AB and AB plane is almost the same, okay? We just say the gamma mix equal to BB plane divided by AB. You can notice that. And what is BB plane? BB plane, we can further using this yellow part to get R D phi as a pizza shape. Okay? And luckily, AB is just dx, right? So R d phi divided by dx. So gamma mix equal to R times d phi over dx. d phi over dx, we name it theta. The theta called twist rate. So twist angle per unit length. So you can see that the units here, the phi here, sorry, the phi here, the unit is not radian. It's not the radian. Radian. Okay? What is the unit? Radian divided by n. Because this dx. Dx is length unit. Okay? So twist rate is theta. Theta equal to d phi over dx. Okay, so theta, because in pure torsion, which means that the theta remains unchanged, is constant, okay, constant. So your theta in the pure torsion case, it should be equal to theta equal to phi L divided by L, okay? So your R max equal to R theta or R phi L divided by L. OK， 好，这边应该 OK 吧？哈，就是这个 theta 不是角度哦，它是扭旋率哦，有点率的感觉 ，rate 的感觉。OK， 所以它的单位不是进度，它是进度除以长度，因为它是渐渐变大的一种的率啦，哈的 rate。那所以说，如果今天它是一个 pure 的 torsion， 就是纯扭，它没有在那边乱扭，忽然大忽然小的这样，都是维持一定的扭力的话，它的扭旋率应该是固定的，所以是 phi L divided by L， 就是最远的那个最远这个值除以它的总长度，那就是它的线性往上变大的扭转角的率嘛，斜率的感觉，就是 phi L 除以 L， 然后 R max 就等于 R theta 等于 R phi L divided by L。OK。Now I would like to say something about the max. I will let you know what does that max mean. Okay. I just give you the answer right away. Gamma max. Why max? Because this element is on the surface. Okay, the max because this is on the surface. If it is inside the body of the bar, it is not maximum. Okay, I will take a look. I mean, you will understand that after the next page, after this page. Okay. All right, so next. Stress in the bar, okay? So you can shear stress in the bar. So you can imagine that this circle, okay, this circle, and you can imagine that outside it should be rotate. I mean, because you have the same twist angle, right? So for the B and B plane, it moves long away, and then in the middle, no rotation at all. The B and B plane at the origin, they are overlapped, right? So you can imagine that it should be like, right? So you can see that in the surface, you have greatest movement, displacement. But in the middle, if you rotate like this, twist the surface, the middle doesn't change at all. The center of the circle doesn't change at all. So you can imagine that its greatest displacement at the surface and then relatively lower with the depth. OK， 越深的地方越小 移动. What does that mean? If you have the deeper the depth of the location, it suffer lower displacement. Okay, which means that your shear stress at the surface is biggest, is the greatest, tau maximum. And at the center, 0 tau at the center. Okay, so you can correlate these two things, obviously, right? So I just copy this figure from here, all right? They are the same. So this figure, we have an element on the surface, and we do the twist. We have gamma mix because this surface element is at the surface. So you have gamma mix equal to r theta. Okay. How about in the middle? So you can see that this is here, right? This is a dashed line. However, if we are no longer r, we become low. The low is the radius less than r, okay? Low less than r, okay? So less than r radius is, we call that low, whatever its value, okay? So maxima low equal to r, okay? So the gamma, not mix, gamma is at the surface in the inner element, kind of inner, okay, the inside the body, okay? This gamma equal to low theta. So you see r theta, low theta, okay? So you can see the ratio between gamma, which is inside the bars, and gamma mix, which is at the surface. What is the ratio between the two? Low divided by r. Easy, right? Just the ratio between the radius of their corresponding radius. Okay, so you see ratio this is ratio of radius. Okay, that's it. Right. So now we are going to see a hollow tube. There's nothing in the middle. Okay, nothing in the middle. So which means that, hey, you only have upper part, nothing here. So of course there's no stress at the middle. Okay, so your gamma mix, of course, R2 phi divided by L. Very similar to the previous one, because at this stage you don't need to see in the inside. Okay, it's just similar. Okay, similar. But R minimum means that here, right? Means that here there's no zero because no element material there, right? So R minimum, gamma minima is here. Gamma minima R1 over R2, gamma maximum. Okay, so very simple, straightforward, nothing difficult. All right， 听得懂哈？表面有最大的剪应力 ，OK？ 那深度最深的地方就是没有剪应力，很正常嘛，看得出来。那最大的剪应力跟中间的剪应力差距多少呢？就根本就是它的 R 的比值，就这样的。Hollow tube 的话，中间当然就没有一样了，就照算就对了，简单。All right, so let's continue. It has Hooke's law too. Okay, shear stress on the surface of bar, tau max equal to G times gamma max. No problem, right? The gamma max equal to R theta. No problem. So tau max equal to G R theta. No problem. Easy. And the what is that? Oh, the shear of the rod is proportional to the distance from the center axis. Well, just like what I said, ratio of radius. Okay, so this tau is not maxima anymore, right? Tau equal to G gamma. Okay, the gamma is not gamma mix, so okay, so your gamma equal to log theta. Wow, so very simple. All right, so just changing, just changing parameters. Very easy. And then I would like to tell you how the torsion generating shear in the bar. Okay, so shear stress in mutually perpendicular planes will exist in pairs to maintain equilibrium. What does that mean? It means that all the shear will come in pair, come in group, right? 所有的剪力都是成对出现的。Okay, so if you just imaginarily cut the bar out of it, there's a one piece of pizza cut off. Okay, and then you see that if you have a stress element drawn like this, okay, and your shear, what does that looks like? Your shear looks like this, right? The greatest will be gamma max. The lowest will be center 0, right? Okay, so I believe, so this figure is actually this one. Okay, I just draw a blue element. You can just only see the one lines here. Okay, this stuff is this. Okay, you just see this area, this line from this view. All right, so you have gamma max, but remember this tau max come in pair, right? So you have this, you have this downward, right? So you must have the other way, tau upward, okay? And the other will be the left. Where? Here as well, and it's called tau max. Here is tau max 2, okay? And it also gradually decrease to the center. Okay? Okay, so you can see that the torsion will cause shear stress at the material point. All right, so you can see that if you have torsion like this, okay, and then torsion and torsion, right? So you will make the element try to become a, you can see that this element will make it like this. Okay, so you can see kind of say that it will compression in this way and stretch in this way. Oh, okay. Right, so along 45-degree will be the less strength. And you will notice also when you go back home, if you have a if you have the towel, if you just twist it and try to make it break, and you will see X shape of the break. Okay, because they are 45-degree direction, it will break it because here is tension and this is compression. All right. So if you can understand this, we are now going to correlate the stress, shear stress, and the torsion. Previously in our chapter 2, we have sigma equal to P divided by A, right? How about our sigma tau? Okay, stress tau, shear stress tau, correlated to torsion. So that's what I'm going to discuss in the next page. Okay, so what is the relationship between the T and the tau? So next page, and I will guide you to show the relationship between the two. And remember, I told you 95% up of the proof in mechanics of materials, they have very similar procedure of proof. The first one, the stress times every area, and do the work balance. Okay, and then you got it. You got the answer. So that's which is exactly what I will do here. All talk about the area times the stress. So everything is the same. All right, very simple. So now let's take a look. So previously in chapter 2, we have sigma equal to P divided by A. You know that, right? Now in this page, I would like to ask, what is tau? And to the T, what's the relationship between T and tau? That's the purpose of this page. And we call that this formula called torsion formula. Okay? I don't know why it's called load formula, but you know, similar. Okay? You can compare them between each other. The area at the radial distance low, which is shorter than R. Okay? There is a general small material stress element called, well, we just say dA. Small dA in the cross section. You can imagine that there's a bar with the torsion T on it, and we just cut it to see the area, cross section area of this. So there is an area, arbitrary area, okay? Area at the radial distance low is dA. And the shear force corresponding to this area is tau dA, okay? You see here. There is a shear at that area, dA. So the total shear force of that area is tau dA. Tau is a shear stress. dA is their area times together become shear force, tau dA. Okay? And remember that the tau dA is a shear force. Shear force is a force, right? How about the T? The T is force times the meter, right? The unit length. So it's kind of force times the distance. Force times distance is T. So you have force here. What is the force arm of it? Low. Okay. So the torque, the small torque due to this area is dt. Small torque due to this small dA area is tau dA, which is shear force, right? And low is what? Low is arm, right? 力背. Okay? So if your arm times its shear force, it is the small torsion due to that particular small surface, the A. So what is tau? Tau is tau mix divided by R times low. Remember that? And the low times together becomes square. Okay? So dt equal to this one. And then I can write down further, okay? Tau equal to low divided by R and tau mix, right? So this tau become how about I change a bit? Can I make it how about I change from this? Okay, the tau is equal to low divided by R, tau mix. So you just substitute this into this formula, and then you can get this. Now you have dt, right? dt is the shear force times the area. Sorry, shear force times its arm. Yeah, but your torsion is on the whole surface, whole cross section. So you need to sum them up, all the dA, every dA in this area. You need to integrate it. Okay, so your T, the total T need to be integrated. The total T is integrating all the small dt on the cross-section area. So T equal to area integration dt. Okay, so your dt substitute here, and this one become constant. Go out to the integration. So you got low integrating a low square dA. Okay, so this one looks ugly. Okay, so I will give you a symbol called I. Okay, called I. The I here is moment of inertia. Moment of inertia in Chinese, 惯性矩. 惯性矩. Okay, 惯性矩. A moment of inertia is a little bit difficult to understand, but I'll explain to you, of course. But if you still don't understand, you can ask my mechanics tutor, because I have asked this question to the mechanics tutor, ChatGPT. Okay, I share with you. It answered quite well. Okay, so you can try that. 听得懂吗？这个惯性矩啊，我之前我觉得有点难懂，那我会讲了哈，没问题。如果你听不懂的话，你可以回家去问问看你的 ChatGPT 的助教啊，我分享给你。我问过哦，答得不错哦，你可以试试看，蛮好玩的。Okay, so let's take a look. And I also want to mention that what is P here? The P means polar. Polar. Okay, the polar means 极坐标. Okay, polar coordination. So you see, polar moment of inertia is called 极惯性矩。极惯性矩。当然啦，极惯性矩就是用极坐标做出来的惯性矩啦哈。那之后我再跟你解释更多东西。好 ，OK, so let's continue. What is dA? What is dA? dA is difficult. what is IP equal to log square dA integration? Well, although it looks really difficult, but actually it's not if I draw with you. All right, draw with you. Okay, the theta, and this is the A, and yellow, and below, and this is log, and this is log d phi, log d theta. Okay, so you can imagine that these pizza-like is actually this one. Okay, and if you're generating the dA here, dA, okay, dA here, and you need to generate dA, you need to open up a theta angle, right? So here, just open up the theta, okay? And then d theta, this length is d theta times log, okay? So you get this one. And the height of the dA is actually the increment of log. So you increment grow your log, you have d log. So log d theta times d log equal to dA. Okay, so I will continue this lecture after 10 minutes. Okay, if you have any questions, just come here. Thank you very much.
有包括的增程，那为什么算总？就是它是用比例扣掉里面这个半径计算这个是它的受力。那为什么不是就是 dBc 扣掉？就是为什么中间这个面积不被看成是？
哦，因为它只有中间是就是那个盖子啊，就是蓝色盖子那种感觉。蓝色盖子盖上去，然后这个盖子只是负责传力到这个管子上。所以只有墙壁在。你当然说那个板子的确是有受力没有错了，但是它要算的应该是这个管子的应力跟应变状况。那个板子它的确是有受力没有错，它是有点这样弯起来，但是那很复杂，我们就没有在考虑它。所以他在问的问题是，就哪里有你想要去算这个板子的这个问题是？
不是，我就是想说，为什么就是那个板子中间的，就是可以，就是它那个面积的受力就是可以不用算。
哦，其实它有应力在里面哦。这个板子是有应力的，只是它没有问吧？它应该是没有问。其实这里面都是有应力在上面，而且它会比较高哦，它还会有这样忽然这样陷下去的红红的这一圈都是。对，它这东西是应力最大的，没错。可以，我不能画。它其实真正在有应力的地方，就如果你真的是用做电脑去画出来的话，它其实这边是红的，我是很红哦，它其实很红的，然后它会这样慢慢的渐层出来。
这外面有最小。
我看一下。
外面会是0。
那我想想看它会是怎么样？它也不会是0，因为它要传递它的力到下面去啊。那所以它就是慢慢渐渐的出去。
就会是0。
那我想想看啊，外面它实心的也不会是0啊，它不会是0。对，好，不好意思，对，没错，你说的是对的。对，它还是会这样子分散出去， 如果是实心的话，但如果今天是空心的话，它就一定会在外面。不好意思。
那现在空心它就是外面。
对，它就没办法，它就没有办法这样子流了嘛。它就一定得到外面去流。你就可以想象它也是水的感觉。大概是这样。好，谢谢。好，请问，好，总之它就是想看哦。总之它就是越下面的力越大，因为它的压力会越大。对啊。然后你就会觉得就是你就可以写出它的函式啊，它的函式也写出来了。
对，可是它的函式跟 y 的关系，为什么就是好像它是可以，因为它好像不是直接 f 乘 y 乘以 y 的，是它是力。
没有 F 就是它的力啊。
但是可能类似，它好像是被分多几个东西。
来，我看一下哦。The friction force produced applies a small force on the surface of the iron。好，看一下 friction。好。Skin friction is uniform. Skin friction varies.
一的话，我不知道要怎么很实习，抽这个意思。
他没有写错，他的意思是说，
没有分，我都要把这个要把
这个已经算出来，对不对？好，那这样听起来是这样子啊，就是说你要算它的力的话，你要切开了它的，切开。
这个好像直接在这上面。
嘿，不行。
还要6点，对吧？
没有关系。这样可以的话，它可以这样切。对，它就是你要切的话，你就例如留上面，留上面的话，就是你的 F 可能就是这么多，然后要乘上它的长度，L 减 Y 之类的。对，我印象中是这样子。那这个的话就不用，像是 constant，但它这边是有变化的这样，所以你要用切的方式，然后把上面去留下来，对，然后去算它的面积，这样，那就是分布载重的问题。
这题要是因为这边算自重的时候是需要再乘以 t，
对，
然后这题不用，想说是因为它这边给的是维持的题。
对，一个是 density， 一个是 weight density， 对 weight density 就已经变成就是 weight， 就已经乘上去过了，对，对。 哦，又来了，你看，我才回去不到，拿个大包又上课了，太太快了吧？啊，好，最近我去大业大学受邀去分享 EMI 的课程，就是上课讲经验这样，然后然后我就觉得说，就那时候他就叫我说，就很多怎么讲啊？这要怎么解释啊？就大学就有很多的那种就是例如说警卫啊或职员啊，反正他就旁边的那些人就会说，哎，以前的演讲者都是全程英文哦，就是 EMI 就是讲解经验分享全程英文哦。我心想说，哇，我要分享 EMI 教学的经验，但是就真的要用英文讲，也就是说，真的跟上课是一样。那他们就说，哦，全程英文啊，全程英文啊，都是这样子的。然后我说，哦好好好。然后我就上台，我就开始讲，这样就全程英文啊。我讲了1个半小时，讲全部都是英文。讲完以后，然后主持人就说，哇，这位老师就是我了，这位老师真是太了不起了，他是我们第一个从头到尾都讲英文的人。然后我就哈，我听到不是这样啊。然后哈，我那么认真，对，就这样，就被骗了，哎，然后他们就是不知道为什么就很多消息就跟我说，哦，就是全英文啊，全部都是英文的啊，每个老师在那边讲都是英文啊，真是，当然啦，没关系啊，但我只是觉得，我还当场我就说，哎，那跟我听到不一样哎，我就是我都很紧张哎，这样很努力，即使是讲再久的 就是有这么多年的经验嘛，就是我从2008年出国念书，然后在那边4年半，在英国4年半，当然是讲英文嘛。然后回国以后，每一年都还是有 EMI 的课程，是规定的哦。你知道我们新进老就材料系，应该说全交大哦，新进老师的聘书上面写说，规定就是你每一年都要至少上一门英文授课，然后还有其他点，就是我都看一下蛮有趣的哦。还有一点不能跟学生谈恋爱。哦，好好好，啊，是。对，所以说就是你每一年都要上 EMI 的课程，跟你不能跟学生谈恋爱这件事情同样重要的是同样重要的，所以我就每年都很认真的上 EMI 的课程，这样好就这样加油好。但即便如此，我还是会觉得很紧张了哈，就是讲英文就是会紧张，毕竟你是讲中文的时候，你就可以很快的选字嘛，对不对哈？你脑袋的词汇量很多，然后你下一句要讲什么，就可以马上选对的字。但英文就没办法，英文就没办法用很好的把关键的字这样马上选出来，我就觉得有点，不管怎么样都还是很紧张就是了啦。那你知道为什么我上课的时候都会比较顺畅吗？那是因为全部都在这里哦，全部都在这里哦，答案全部都在这里。其实你看我在那边写，好像我脑袋在转，对不对哈？但实际上我脑袋一片空白，我就只是负责抄而已。好啦，也没有那么糟啦，但是终究还是要知道在讲什么。但我只是说东西都在这里，我就不用去思考，就是说，我写的东西是不是对的或错的。所以我反正就讲过去。那我在写的时候，就顺便可以思考我等一下要讲什么。所以实际上，真的还就是这样的教法是对我来讲是比较顺畅的。那你知道 Good Note 5、Good Note 6，它可以录制我的笔记吗？知道？你知道它可以这样录吗？它连声音都可以录。所以我一直很想要做一个实验，就是实际上我已经把今年我就把它录好了。然后明年的时候，我就嘿，各位同学，我开始上课喽。然后我就开始播放，然后我假装我在写，假装我在写，然后我嘴巴在那边对嘴，他就一直在讲。我要看你们会发现，如果可以这样的，我每年就是这样，然后站在那边2个小时，然后假装他自己那边动，然后就演讲就出来，多好，对不对？这样不错吧？我真的想要实验看看，哪一年现在开始录好了，这可以录哈，我看一下，这要怎么录啊？哎，还是不是 Good Note， 是那个 Notability 好像可以录，看一下。Anyway，反正好像有一个东西是可以录，连笔记都可以录，吓我一跳。好，好了，讲完了，开始。So I just talk about how we use DA, how we represent DA, okay? The DA is just like, so maybe I can draw the same color here, okay? Yellow part. The yellow DA can be represented by low d theta times d theta, d phi, d low. Okay, so if you can accept that, we can 0 to pi 0 r low square d low times low d theta. Okay, so the d low times low d theta is the dA equal to 0 to pi 1/4 r 4 d theta equal to pi r 4 divided by 2. Okay, so our IP here is pi r 4/2. Polar moment of inertia of circle, of a circle shape cross-section, pi r 4/2. Okay? And the polar moment of inertia of a circular section with respect to the center of the circle. So you can see that the detailed definition is these words. All right, you see the polar moment of inertia, IP, of a circular section, with respect to the center of the circle, Be careful, because the moment of inertia is how you rotate about a shape as well as its origin, okay, or the axis. Later I will tell you. So this rotation is about the center, okay? So you see, center of the circle. So your moment of inertia not only related to the shape, but also related to the axis of rotation itself. 讲中文就是说啊，惯性矩这个东西啊，不只是跟它的形状有关，还跟它对于哪个轴去转有关。像这个极惯性矩就是对着这一根轴，初直面这根轴来旋转，它的值叫做派 r 4次方吹耳。Okay, so how about other shape, other rotational axis? Don't worry about this. You have appendix D. Okay, you will see the appendix D in your textbook, where it said IP equal to pi r 4 divided by 2, or you say pi d 4 divided by 32. Okay, I will rearrange a bit. Don't worry about that. Okay, you know D is diameter. Okay. Now let's go back to the here pi r. Pi r 4 divided by 2. You can substitute this here. So or substitute this pi d to 4 divided by 32 to here, and you can get tau mix equal to tau mix times IP equal to TR. Okay, so this is the torsion formula. So your tau max equal to 16 T over pi d3. But this one only suitable for circular cross-section. All right, tau max equal to TR over IP. TR over IP. Or the shear stress at the distant low, of course, tau divided by T low divided by IP. So you see R low. Low is a smaller radius related to the R. Okay. That's it. So we successfully connecting tau and the T, because T is what you apply to the bar, right? You know the value. And then you can, using this torsion formula, you can determine the shear stress in the bar or at the surface. Okay. Now I'm going to introduce further about moment of inertia. Okay, moment of inertia is really important, and it will be used in chapter 5. Chapter 5 is the most difficult chapter in mechanics of material. Okay, I will So please be careful about the next page, moment of inertia, 惯性矩. And in the next page, I will give you more Chinese version of the moment of inertia because I add sectional moment of inertia, 截面惯性矩. I just want you to know that the moment of inertia is really depending on the section shape and also the rotational axis. Okay, next. So what is moment of inertia really? Simply speaking, is that how difficult of that shape rotate to that axis. Remember the inertia. Inertia is easy, right? 惯性. I believe you know that. What is the inertia? If you have a really heavy mass object, heavy, really heavy, which means that you are difficult to push that object toward, right? You cannot push that. I mean, you need to pay. This is if the mass is inertia, right? Mass is big, which means that you are difficult to move it. How about moment of inertia, which means that if the moment of inertia is big, it's great, which means that you are difficult to rotate it. That's it. 听得懂吗？一般的惯性就是质量，你的质量越重，越难推动它，因为它越懒惰，想要惯性在那里，对不对？那 moment of inertia 就是这个东西越难被转动，就这样而已。OK， 那越难被转动，你可以想象嘛，就是有的东西你对某个轴比较好转，有的东西对某个轴比较难转。我等下就会给你一个非常好的例子，我每年都是举这个例子，大家都会听懂。Okay, so very important concept. Moment of inertia is that something that measuring an object or cross-section, how difficult it is to move it. Greater the moment of inertia means that more difficult to rotate. All right, so let's continue. How to define the difficulty of rotation. So this is the area here, okay? I want to see this area rotate about x-axis. Okay, this is x-axis. And it will rotate about the x-axis like this. Okay. Okay. So how difficult it is. So you see rotation Ix. Ix is the moment of inertia about x-axis. Okay. Rotate about x-axis. So you see how it rotates. So you can imagine that this area rotates about x, the direction, sorry, the distance between this area to x is actually their y coordinate, right? So this is y squared, okay? And if this is blue, which is y-axis, and it will rotate about the y. Okay, rotate. So this area rotate about the y. Okay, so this area to the y axis, the distance is x, so x squared. Okay, and we are not talking about the shape because we're still using its general form because we haven't done the integration. Okay, so this is a definition. It is. And remember IP, the polar moment of inertia in the previous page. It is rotate about the O, right? Rotate about the O. So you see this is the radius law. The law is actually the x squared plus y squared divided by, right? It's a 毕氏定理，我不知道英文怎么讲啊。So the law square equal to x squared plus y squared. So actually you found y squared, x squared. So ix plus iy is actually ip. So that's a relationship between the ix, iy, and ip. Okay. So now I believe you understand what is moment of inertia. And then I'm going to introduce other shape. Moment of inertia for a square. It will be used in chapter 5, okay? And this is one part of the appendix D looks like, okay? Appendix D providing many shapes and many axes, okay? And this is the result. And you see here is about centroid, and this is about ix, iy, and this JC is actually IP, okay? This is IP, polar moment of inertia. Right. Now, let's take a look. How to use this table, how to use this appendix D. You see this shape going to rotate about x-plane. X-plane. This is x-plane axis, not x. X is here, y is here. So ix-plane is going to here. So this rectangle will be rotated about x-plane axis. You see, this is 1/12 BH cubed, okay? B and H cubed. So it's related to its shape. It's 1/12, right? And then let's take a look. Really interesting stuff. Ix. Ix means that this shape rotate about x axis. What is the value? 1/3. So tell me, bonus, okay? Which one is easier to rotate? Which one? Please tell me. Anyone? Which one's easier? Remember the what? 最上面那个 Tell me English. Speak English. The first one. The first one, which is ix plane. Ix plane. Or which one? Ix plane or ix? Ix plane. Yes, exactly. Please let me. Please tell me your number. 613. 0, 0, 9. 9. Okay. So you're right. This is easier. This is not easy. I will give you a straight example. This is the square. Okay, this iPad is a square. So I'm going to rotate about IX plane. IX plane, which means that about the centroid. What is centroid? 行星啊 centroid. So this X plane looks like this, right? So let's take a look. Do you think it's easy? Quite easy, right? How about X? My hand, my arm is X. Okay, let's rotate about this. What do you think? Which one is difficult? This one is difficult, right? And this one, easy. Okay, so that's the moment of inertia means. That's it. I really think this is really nice example, and yeah, I'm quite proud of myself. I can figure it out this example, and then I believe after I demonstrate that nobody will doubt which one is easier or not or difficult. Yes. All right. So let's continue our lecture. Angle of twist. From Hooke's law and torsion formula combined together. So you got theta equal to T over GIP. And we said GIP is torsion rigidity. Okay, anyway, just another terminology, not important. And in pure shear, theta is unchanged, constant means that constant theta equal to phi divided by rho, and phi equal to T divided by GIP, and GIP is torsion state, blah, 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 blah. Okay, anyway, it's not important. These procedures just, I believe you understand this procedure, just substitute all you know, and then you can get this result. Right. I want you to take a second look about this phi equal to TL divided by GIP. I will write down a formula that you are quite familiar with. Delta equal to PL divided by EA. And I would like you to compare these two. Delta and phi. P, T, L, L, E, G, A, I, P. All right. So comparison. Actual stiffness, K equal to EA divided by L. You know that. So torsion stiffness, GIP divided by L. So you can imagine that this A is actually equivalent to the IP, just like your actual force. All right. So very, very similar. Okay. So if you can understand this, your phi equal to TL divided by GIP. So please, wow, memorize it maybe, and don't forget that this GIP, the IP here, that is a polar. Okay, and the torsion formula you you show that based on circular cross section. So if you are saying phi equal to phi of a square bar, no, you shouldn't apply this. Sorry, you shouldn't apply this. Okay, because this is not for a square cross section bars. Okay, but it does apply circular tubes. So phi equal to TL divided by GIP. Okay, and then this is the R1, R2 tube, and the thickness equal to R2 minus R1. Okay, so your normal tube IP equal to a normal tube. So you can see half pi R2 powered by 4 minus R1 powered by 4, which means that you can imagine that actual solid IP minus this hollow, empty space of IP。OK， 这样听懂吗？就是管状的东西的 IP 其实比想象中的简单，其实就是把你想象它是一个实心的外围的，减掉它内部面积的相对的 IP 就好了。那为什么呢？因为它是用面积来去积分的，那就把面积减掉就好。所以其实还蛮直观的。So, if you have a area like this, you can freely how to say that, minus the empty space area. Okay, so you can just take out an area and simply minus the corresponding IP, because all this I done by the area integration. So if you have, you can even imaginarily treat this area as minus area value. Okay, and this is the positive area value. Okay, sum it together. 你甚至可以把这个中间这个白色部分想象成是负的面积，把它加起来，就把它扣掉，这样。Okay. And another thing is that thin wall tube, it looks like this. Well, this is just another, it is introduced in the textbook, although it is really difficult to, it is not easy to see that by your first glance. Okay, so I just give the really quick say that calculation. All right, so the thin wall tube means that T is really small, which means that R2 minus R1 is really small. Okay, so the IP, the real IP is half pi times R2 4 minus R2 minus T 4. So R2 minus T is R1. I believe you know that. So if you just expand the equation and neglect T4 and T square terms, and you can get this one. All right, that's it. It's not difficult. Just do the expansion and neglecting T4 and T2. Why we neglect T4 and T2? Because T is really small. So after you do the power by 4, power by 2, it will become smaller and smaller and smaller. So yeah. Now, why we are going to focus on circular tubes? Why we introduce circular tubes? Because as you can see, when we do the torsion, we have the shear looks like this, right? So outer surface has maximum, but inner surface has minimum, and in the middle even 0, tau equal to 0. So you can imagine that if your material should place at the more sufficient position to resist the shear, right? So it is more reasonable to put our material outer surface, because the surface, the material can resist this shear stress. But here, very low shear stress. So actually, if we put the material here, it's a waste. It's a waste. Okay, so hollow tubes are more efficient than the solid bars in resisting a torsion. Okay, and the hollow tube is lighter and less material are needed, so you can cost less money, less expensive. 听得懂吗 ？Tube 是比较中管是比较省钱的方式。你可以看到，我们花钱买材料是要放在刀口上，这边就是刀口，这边就不是刀口，根本不太重要，因为它根本就很小很小的 stress， 对不对哈？所以放材料，放一样钱的材料太浪费了啊！除非你里面放纸啊，或者放一些棉花，那就算了，就比较便宜的东西。但是说实在的，就里面的东西是 material 是不需要，尽量是不需要放的，因为反正它的 stress 也很少。Okay, limitation. Again, I told you in the previous few slides that because our proof is based on circular cross-section, okay, either solid or hollow, and also linear elasticity because we apply Hooke's law, right? So these formula not suitable for other shape. Now let's continue. Let's take a look about how efficient of a tube. Given the T here is 1,200 Newton times M. Okay, so this kind of rotate this or rotate this. One is solid bar, the other is hollow tube. Okay, and allowable tau here is 40 MPa, and allowable rate of twist theta is 0.75 degree divided by n. Okay, so your rate of twist cannot exceed 0.75 per meter. Okay, and G is this one. Okay, so find a D0. You need to design a D0 to subject it to this big torsion and not break. Okay, that's what we are going to design. And D2, if the T equal to D2 over 10, and then we will compare the weight of two systems, okay, to see which one is efficient. Okay, so let's take a look. One, I know you know the answer, right? But I would like to show how efficient it is of the tube. Okay, solid shaped. Tau allowed. Of course, we should provide tau maxima, right? So TRIP. We shouldn't use T low IP because we are going to see the maximum stress, shear stress place, not exceed tau allowed. Okay, so TR over IP and T times D naught over 2 divided by IP. IP is pi D naught 4 divided by 32, which is 16T over pi D naught 3. So minus 40 why minus? We don't need to, right? 40 times 10 to 6 pa equal to 16 times 12, 16 times 1,200 and the pi D03. So D naught equal to 53.5 millimeter. Okay, and this is tau allowed. How about angle of twist theta 了 theta 了 okay theta T divided by GIP, right? GIP equal to T divided by G high D naught 4 divided by 32. Okay? And 0.0131 equal to 1,200 divided by 78 times 10 to 9 times pi d naught 4 divided by 32. Okay? So d naught equal to 58.8 millimeter. Okay, so solid shaft. Which D we like to choose? Which D would you like to choose? Yes. The bigger one. That's really nice. Bigger one. This one, right? What's your number? Okay, good. Yeah, we need to choose the bigger one. Choose the bigger one. Okay, because because we are going to choose the reason why we are going to choose the bigger one is that here is the diameter. If we choose lower than 53.5, it will shear break. If we choose the diameter lower than 58.8, it will rate of twist break. So we need to prevent this, right? This is a higher criteria, all right? So we need to put, we need to choose this. Right, second is hollow shaft. Hollow shaft. D1 minus D2 minus equal to D2 minus 2, 0.1 D2. Yeah, we need to be careful. You see, we need to time 2 because because D2 and D1 has double space of the thickness. We need to have 2. Okay, be careful about this. And IP equal to pi 3 over 2. Sorry, pi over 32. D2 4 minus D1 4 equal to pi over 32. 0.5904 D2 4. Okay. And equal to 0.058 D no 4. So tower loud. So firstly, we need to determine the IP because this is the hollow shaft. And T times D2 over 2 and over 0.058 D04 equal to, so D2 should be D2 should be 63.7 millimeter. How about angle of twist? T over GIP equal to 1,200. 78 times 10 to 9 times 0.058 D04. So we can have I love digital blackboard. You see, I can make space freely. D2 equal to 67.1 millimeter. Okay, so you see 63.7 and 67.1. We will choose the bigger one. Da, 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 da. So our D2 equal to 67.1 millimeter. But maybe you will say, hey, you said tube is more efficient, but it's bigger than 58. Of course it will be bigger, but this is not the way we calculate the money. We calculate the money by weight. Okay, so this is the third problem. The third problem here is that we are going to determine the ratio of diameter D2 over D0. We know that D2 over D0 is 1.14. No problem. We know that D2 is bigger, but how about the weight? The weight hollow and weight solid is actually A hollow times L times A, how to say that? Cause C, right? I don't know. This is just the density, all right? This is the density. And we assume that the density are the same. We assume that the material are the same so that we can compare, right? So, after that, 0.47. So you see, wow, your weight of hollow shaft is less than 50% weight of solid shaft. Okay, you can save more than 53% weight. Very good. Okay, you can save a lot of money, and your boss will like it. Well, you will like it because if you are a boss. Right, that's it. OK， 听得懂吧？哈，这应该不用讲中文啊，我相信你们应该听得懂。OK， 明天我不会在了哈，因为明天大家就考试就好了，然后考40分钟。那大家加油，不是都跟了哦，不能这样讲，就是跟习题非常类似哦。你就把习题做完，每一题都懂，你就会考得很好这样子。OK， 你知道当老师就是真的是不能把话讲得很死，因为有几年我就是太傻，我就说小考跟我勾的题目都一样。然后就完蛋了，就有一次就不小心出不一样，然后就被骂的要死，然后就要送分。所以我们现在就是以后都不讲死，我们就是说会很类似啊，或者会怎样啊，免得出一些包这样，然后把自己绑手绑脚。你知道做事情哈，越老就越有经验，那这样听起来就是有点滑头，就是滑头，就是觉得我就没有讲清，我故意没有讲清楚，这样避免自己被自己的语言绑死，这样。所以，对，然后之前还有一次很好笑哦，我有一次直接应该是固态热力学吧，还是材料力学，我忘记了。有一年应该是2017还是2018，忘记了。我直接把去年的考卷、期中考卷拿出来，拿着这次考，我不是故意的。我出好一份考卷，然后我传给助教印，我传成去年的考卷，然后我也没发现，居然没发现，就印出去考完了，然后就有人传说，就传讯给我说，老师，你今年的考卷跟去年是一模一样。我说真的吗？然后一看，我传错了，没有人告诉我，而且他那个上面的数字就是2017年的。你如果是今年是2018年的话，你就拿到考卷上面写2017年，然后那个日期也不一样。 然后我就哇，真糟糕，我明明就已经出好了，我都出好了，总不能叫大家，然后就有两派，一派就是认真的，也不是，就是有一派就是很认真的会去写考古题，然后当然就几乎都要是满分嘛。那有一些人就是没有拿到考古题，但是他也很认真，他有考试，他有考90几、80几这样。但是这时候就让我陷入一个非常困难的状况，我总不能说重考一次。那些人就是说，哎，我考了100分，我就不算了，很可怜。大家觉得怎么办？怎么办？我真的那时候就是睡都睡不好，因为我要给各位同学一个交代，怎么办？哦，想超久。这时候我想了一个非常复杂的解决方法，告诉大家，我就说我要再出一次考卷，然后呢，这个考卷我会先讲解一个题库，我讲解题库哦，所以大家都大概都知道怎么写，然后这个考卷就会跟这个题库非常类似，其中几题。再来，你考完这个试，这2次考卷分数高的那个，我就选那个来记。很复杂吧？到最后大家就考试，有些人就不用考，因为考100分了，就第2次就可以不用考。但是有些人考不满意，他就考第2次。然后第2次我有先讲解过，所以也算是有一点点像是在做期中，就是在做考古题的感觉。反正我就弄到后来就是终于平安的解决这件事情了。好，就这样，下课。iPhone。对，你说的对，谢谢。告诉我，哎，你可以有那个加分哦。哎，这是你刚刚回答的，不是？哦，好，那你再告诉我，这是你刚刚跟他说的啊，你这么拾金不昧啊，一人加一个哦。好了，对，因为你拾金不昧，值得嘉许，复制2次，然后再来一个1116 double nine，也快记起来了，很好，谢谢大家，谢谢。